There we go. Everything developers need to know about integrating JSON into the Oracle database. And what we covered here is two parts of our JSON functionality. The first part is, if you're an application developer and you want to build NoSQL style applications, how can you do that without losing all the advantages of the Oracle database? And as we'll see in a moment, the answer for that is something we call SODA, Simple Oracle Document Architecture, which is a specification of an API that lets you build NoSQL style applications that use JSON documents for data persistence. And it's a very simple API, similar to what you would see with a NoSQL database like a Mongo or, if you're in the cloud, a Cosmos. But instead of storing data in a simple NoSQL database, it stores data as JSON in the Oracle relational database. And this gives you the benefit of all the flexibility and ease of development that you see with a NoSQL style database, combined with all the enterprise capabilities and queryability of the Oracle database. So the third part of this slide is the big differentiator between using Oracle and using a NoSQL database, which is, with a NoSQL database, you can build an application quickly, you can deploy the application quickly, you can make changes to the application quickly because it's using JSON persistence. All of that is true if you build your application using SODA and the Oracle database. You don't lose any of the flexibility benefits, and you don't have to learn any SQL to build the application. But when you want to perform queries and reporting on the data your application has persisted, you still have the full power of SQL available to you to do that. So we're not throwing the baby out with the bathwater when we adopt SODA and NoSQL style applications. With a typical NoSQL database, yes, you get a powerful, flexible application development environment, and you have little or no querying reporting capabilities. With SODA and the Oracle database, yes, you have a powerful and flexible application development environment, and you have the full power of SQL for reporting and analytical purposes. So let's take a look at that in a bit more detail. So our propositions, is basically we're supporting NoSQL application development on top of the Oracle database, and our aim here is to combine the flexibility of JSON with the strengths of the relational model. We're going to avoid all the costs and overheads associated with polyglot persistence, which is what some organizations end up with, where they have some applications that use NoSQL databases to store their data, and some applications that are using relational databases. And then unfortunately, they find they have applications that need to use both. And now they have a very complex problem of building an application that accesses both kinds of data. And even if they can build the application, keeping the databases in sync and preparing disaster recovery, having a disaster recovery plan that will deal with recovering two separate databases can become very, very complex. That's the downside of the polyglot model. They may claim they give you, optimal support for each kind of data, but trying to manage it becomes a real headache. With Oracle, we believe that we can give you the benefits of polyglot persistence. You can have a best-of-breed NoSQL database, a best-of-breed XML database, a best-of-breed spatial database, a best-of-breed text retrieval system, and a best-of-breed relational database, and they all happen to be the Oracle database, so you don't have a polyglot persistence problem. And we enable the full power of SQL reporting and analytical queries to be applied to your JSON documents. Please do feel free to interrupt me as I go along here. It'll make the session much more enjoyable for all of us. So, looking at the capabilities of Oracle 12c, we basically store JSON as varchar, clob, or blob. When we built the XML processing, which I'm also responsible for and happy to take questions on if there are any, we built an XML data type, and that had certain advantages, but it also caused a number of problems. It took us a long time to get all the other features of the database working with XML. So, it took a long time to get replication, logical standby, physical standby, ... all working properly with the XML data type. So when we started building JSON, we looked at this and said, adding a new data type is complex let's see if we can just work with the existing data types. And so we went to the standards body and we talked to IBM, who also were, looking at how to integrate JSON into the database. And we said, our experience on introducing XML is the last thing we want to do is introduce a new data type. And IBM said, thank God. Clearly it had been just as big a problem for them. So with JSON, we decided that we would store it as varchar, clop, and blob. And we would simply use a constraint to ensure that the content of that field is JSON. We wanted to make it possible to query and update JSON documents using both SQL and PL SQL. And clearly, it's not just you have to store the documents in the database and be able to query them. We need to be able to optimize those queries. And we want to make sure we could use all of our query optimization capabilities, indexing, in-memory, and Exadata with the JSON data. One of the interesting things that we realized is that one of the problems people face with JSON is it's very flexible, and they basically have no idea what they're storing. So we wanted to give you abilities to discover information about the structure and content of your JSON documents. This is something we call the JSON Dataguide, which I'll talk a bit about a little bit later on. And we wanted to be able to generate JSON documents from your relational content. Some of you may be familiar with our XML capabilities, where we can generate XML documents from relational data. Well, we've added similar capabilities for JSON, so you can generate complex, deeply nested hierarchical structures in JSON directly from a SQL statement. And we wanted to integrate JSON with the other types of content that we store in the database, the multi-model database, as distinct from a polyglot model. So let's talk a little bit more about SODA. SODA, as I said, is something for the application developers. Those of you who are DBAs are undoubtedly hearing from the application developers that they don't want to be writing SQL, they don't want to learn SQL, they don't want to learn JDBC. These APIs are complex and difficult to understand. They want something that's a much simpler approach to application development. And that's what SODA is. It's simple Oracle document access and NoSQL style API for the Oracle database. It gives them the ability through the API to create and manage their collections of documents, to insert, retrieve, or create, retrieve, update, and delete operations on those collections, to list the contents of the collections, to search the contents of collections using query by example approach, and then utility and control functions for allowing things like bulk inserts and index management. So the SODA specification lays out an API that's a very simple NoSQL-like API that gives developers the ability to do all of the things that the application needs to do in a very simple and straightforward manner. Developers can develop against SODA and work with Oracle without having to learn SQL or without having to call the DBA every time they need to create a collection or drop a collection. It basically gives them that same development experience as a pure play document store. SODA can be used to store JSON content and binary content, where binary content is anything other than JSON. And it's currently available for Java. There's a Java API and a REST API. And we're working on other implementations. In fact, with 18.1, we have delivered the initial versions. They're not complete implementations of the specification yet, but the initial versions of SODA for PL SQL and SODA for OCI, or for the C programmers. However, currently, no matter what programming language you're working in, the chances are it can make a REST call. It can issue an HTTP request. And that's why one of the first releases of SODA was SODA for REST, because using SODA for REST, you can basically invoke SODA and talk to an Oracle document store from just about any programming language. And yes, I did actually do it from COBOL just to prove it could be done. I wouldn't recommend it, but it is possible. SODA for REST is fundamentally a collection of microservices for working with JSON collections and JSON documents stored in the Oracle database. Like most REST models, it maps a URI pattern onto an operation on the document collection. And as I said, it can be invoked from almost any programming language you can think of. As long as that language can make an HTTP request, it can invoke SODA for REST. The delivery mechanism for SODA for REST is it's delivered as part of Oracle REST Data Services, ORDS 3.0 and above. So basically, to get SODA for REST, you simply download ORDS from the Oracle Technology Network. It's a free download. You configure it to connect to your database, and you're up and running. And basically, it just consists of a series of HTTP requests and responses with JSON payloads. One thing to remember about Soda for REST, it's HTTP based. So basically it is stateless. There is no transaction support in Soda for REST. Each operation on your document store is atomic. Will you excuse me 1 second? I didn't intend talking for the entire session and I'm running a little dry. I'm just going to grab a water. Okay, so give you an example of what Soda for REST APIs look like. We map a schema as a container, as the container for your collection. So an Oracle database schema can contain one or more collections. Soda root here is a virtual URL that can be a number of different shapes depending on how ORDS has been installed. But fundamentally, at the end of the day, it's something like, ORDS, schema, latest, Soda, then schema. ORDS, schema, latest, Soda will get you the list of collections in a schema. If you then do a list, a get on a particular collection, so you add the collection name to that URL, you'll get a list of the documents in that collection. If you then add an ID to that URL, you will get the document associated with a particular ID. To create a collection, you simply do a put on the collection URL. To update an object, given its ID, you do a put on the collection URL with the ID. To insert an object into the collection, you simply do a post to the collection URL. And then post is overloaded with some things for other functionality like QBE and indexing, as we'll see later. Here's a simple example of how easy it is to use Soda for REST from Node.js. This is actually using the request npm package, and I simply set up the request options. I'm doing a put. I've got a function in my node that knows how to find my document store URI, the base URI for the document store, and I simply append the collection name to it. I tell it that it's going to send application JSON. The content type of the post is going to be application JSON, and I add the JSON document to the request object using the key JSON. I can then simply invoke Soda for REST by calling the request function that's provided by the request promise native npm package, and passing the username and password via the authorization option. And what I'll get back is a JSON document describing what happened. Assuming the operation succeeded, it will have assigned a key to the document and give me back that key. Soda for Java, very similar idea. It's a collection of Java classes that implement Soda and can be called from Java. It has classes for collection management, for performing CRUD operations on the documents, for doing query by example, and the utility and the control functions. And the advantage of Soda for Java, say compared to writing a JDBC program, is it's much, much easier for the application developer to build the application. The only bit of JDBC you need to know in order to use Soda for Java is how to connect to the database. This allows us to, so we basically ride on the JDBC connection so we can take full advantage of the JDBC pooling and other functionality. By default, a JDBC connection is non-transactional. It's in auto commit mode. So by default, Soda for Java would be in auto commit mode. But with Soda for Java, you do have the option of turning off the transactional nature of the auto commit nature of the JDBC connection, in which case you can now have multiple sets of Soda operations part of a single logical transaction. You manage the transaction through the JDBC connection. The other interesting thing about Soda for Java is, back to my point about the advantages of multi-model versus polyglot, is you can actually have a transaction that covers operations on your relational data, operations on XML data, assuming it's in the database, operations on spatial data, operations on textual data, and document store operations can all be part of one logical transaction, what we term the hybrid model. And Soda for Java is an open source implementation distributed via GitHub. So if you want to start playing with Soda for Java, you simply go to GitHub and download the jars, and if you want to, the source code from GitHub. Here's a simple example of inserting a document in Soda. I'm going to use JSON here, which is Google's Java object to JSON mapper, to basically take in a JSON object, and then I get my collection by opening the collection, and I created an Oracle document instance using JSON here to convert my JSON object into my Java object into JSON, and then I create an Oracle document from that JSON string, and I simply insert and get to store it in the database. If you considered trying to do all of this in JDBC natively, you'd be writing many, many lines of code. You can see here the advantage of Soda. If you want that simple document store API, we have 3 calls to insert a document into a database, and that includes opening the collection and generating the document itself. And 1 call actually does the insert. I've talked about query by example. This is how we query our database, and we simply submit a JSON document to the database that describes what we're looking for. Here are some simple examples of the Soda QBE language. In the first case, I'm simply saying I want to retrieve the documents ordered by the release date key. In the second case, I'm looking for documents where there is a location object with a city key that contains the value San Francisco. In the third case, I'm looking for an ID attribute that matches one of the values specified in the in key, or the array of values associated with the in key. I can do full text searching. I can put multiple predicates into a single query. So here I'm looking for movies with the ID of 10109410 and a start time in the range specified using greater than, equal to, and less than, and I'm ordering by a couple of the other attributes. And we also have full support for spatial searches using Oracle spatial technology on documents that contain GeoJSON encoded points, lines, and polygons. As I said, Soda for PL SQL and Soda for ACI, restricted availability functionality available with what was the next release a month ago, but is now the current release, 18C, currently available in the cloud only, but basically allows you to do CRUD operations on Soda collections from PL SQL, but currently at the moment has limited support for QBE and other bits of Soda. We're hoping that stuff will come out in the not too distant future, hopefully before the next major release of the database. The main reason for having OCI is it's going to allow us to build a series of drivers moving forward for other popular scripting frameworks now that we have the basic OCI connectivity from Soda. There is a sample of all of this is available on GitHub and actually on NPM for the Node version. And you can download and run the Soda for an example using Soda for Node, which uses a Soda for REST, Node application that uses Soda for REST and ORDs to talk to the database. And there's also a Java version that basically provides the same kind of API as the Node application, but it uses Jersey to provide REST services and a straight Soda for Java connection to talk to the database. We can take a quick look at that application. I will just start it up now. Find my DOS prompt.
Can you share that part of the screen, please?
Yeah, I would. Just let me get it started. Here we go. Why not? Share desktop 1. Got it now?
Yes.
Yeah, okay, so that was just me firing up ORDs. I'll just kill it and start it again. There we go. So there goes ORDs. And now in this one, I'm going to do node modules, Oracle movie ticket demo, index.js. Oh, sorry, I've got one running already by the look of it. 1 second. Try that again. There it is. Get rid of that one. You can edit that out, can't you, Steve?
Sure.
There we go. So now it's running, and here is our movie ticket demo. HTTP:// localhost 3000. Okay, so let me bring this. Oh, I can't. Okay. I'll just bring the PowerPoint to the front so we can look at what's going on here. So we're looking at this architecture in effect. Actually, slightly different. We're looking at HTML5, JavaScript, and Angular-based front end, consuming REST services provided by a Node application written in JavaScript, which is using Soda for REST to talk to ORDs, which is then in turn actually under the covers using Soda for Java to talk to a document store managed by the Oracle database. So I bring the application back. Where'd it go? What we have here is a very simple Fandango-like application. I presume most people on the call are familiar with Fandango. It's a way to order movie tickets. I think my data is probably stale. Let me see. So if we look here, we can see that we have a list of theaters. And okay, maybe I did update the data. Let's go forward to today. Okay, let's go to tomorrow. So we go back to our list of theaters. We can see that we have the Roxy Theater in San Francisco. We drill down on this and we can see that it's showing these movies. And what I want you to see here is that at the bottom here, it's actually showing the operations that were done to get the data. So you can see here to get the movies for this theater, I did a get on the movie schema and the theater collection with this particular ID, which was the internal ID. And once I got that, I did a query by example looking for movies on the screening collection, looking for movies for theater ID 30, start time between these two dates. And having got the list of movies, I then did a get on the movies collection, looking for the movies that were showing in the theater on that date to get the information about the movie. So this application not only, shows you the kind of thing that you can build very easily with Soda for REST and Node, it also shows you what it's actually doing, what are the requests that are being made via Soda for REST in order to get the data from the database. And if we want to, we can select a movie and book a ticket. And now what you'll see here is that, we did a get on the movie, and then we did a post to log the ticket sale, and a put to update the fact that we had sold some seats in that particular screening. So it's a very simple model. As I said, the code is all available on on NPM. Just look for Oracle Movie Ticket Demo. And there is also a Java version of exactly the same front end. The front end is identical, but it shows how you would build the application using, in this case, Jetty as a web server and Jersey to provide the REST API and Soda for Java to talk to the database. And the point about this is that it's exactly the same front end, operates with either of the two mid-tier architectures. Okay, I'm going to try and go back to my desktop 2 now and continue the presentation. Are there any questions at this point? I'll leave the board.
So Mark, there was a question from Tim. I don't know if you can see it in chat.
No, hang on a minute. I haven't got the chat window up. Okay, I'll see. Go ahead, chat. So Tim, one of our challenges is reaching the developers who are not Oracle developers. This is something that Steve and I and the rest of our colleagues discuss all the time, is how do we reach the people who are not the Oracle developers? We're very good at talking to our installed base. We have more of a challenge talking to the people who aren't using Oracle today. Steve, to some extent, this is more your area than mine.
Well, I suppose, but I don't know how much we need to spend the office hour session talking about that, which is more a question for Oracle than for folks who are here to learn about JSON. So I suggest we table that for a conversation directly with Tim. I mean, in general, what I encourage database developers to do is reach out to the UI developers, because they're the ones who need JSON and work with JSON all the time, and make clear, show them that we can actually provide the information they need in the format they need rather easily, using our powerful SQL features that you were showing before.
I mean, this application is designed to show to them that, yes, they can build a fairly complex application without having to write a single line of SQL, in exactly the same way that they would build the application were they talking to a Mongo or a Cosmos or even possibly a Dynamo. They don't need to know that the back end is Oracle to build this application. They don't have to worry about all the things they might be concerned about, building an application on top of Oracle. Soda really does insulate them from all of that. Okay, so let's try and move on. I should probably have done this slide beforehand. This is the data model that we were using here. We basically have 4 collections of data. Interesting you think that, Judith. Judith commented that writing all the non-SQL part of such an application is much more complicated than learning SQL. I'm afraid in general the industry disagrees with you, Judith. Rightly or wrongly, people have decided that the NoSQL databases provide a simple and more intuitive API for application development than the SQL databases do. I'm beginning to agree with them now that I've built some stuff using Soda and looked at some of the competition. But our point is, if you want to build that way, build the NoSQL style. If you want to continue building SQL, build the SQL style. You can do either with Oracle, which has to give you better choices and better options than locking yourself into one stack or the other. Tim was asking about XE. Yes, there's no reason at all why Soda wouldn't be included in the next version of XE when it becomes available. Unfortunately, I don't have any information that I can share as to when that will be, but I know it's being worked on. So I'm not going to spend a lot of time on why you would use Oracle. I'm going to assume that most of the people here understand that. But fundamentally, by using Oracle as the database to manage your documents, you get the multi-model, where you've got XML spatial graph and relational. You get the enterprise grade features for availability and security, high scalability and performance, Exadata and RAC if you need it, and it's all available in the Oracle Cloud. So all the benefits of the Oracle database, you've adopted the NoSQL style application development and you're getting the benefits of that, but you're still getting all the benefits of the Oracle database. You're not throwing the baby out with the bathwater. All the power of the database for indexing and querying, and transactions and ACID consistency, scalable performance, all the capabilities of the database are still available. With 18.1, we also support the sharding, so we can push SQL JSON operators and simplified syntax with code written using Oracle's simplified syntax for JSON out to the shards and coordinate it through the shard coordinator. All of the operations on the JSON can be pushed out to the various different shards in a sharded environment once you have Oracle 18c. So at the moment that would only be in the cloud, but once 18c becomes on-premise, you'll be able to use sharding in conjunction with JSON. And from what we've seen, our scalability testing showed that we are scaling pretty reasonably across shards. For 2 nodes, we got 1.97 throughput, against a potential maximum of 2. For 4 nodes, we got 3.64 against a potential maximum of 4. So we're pretty pleased with the way that we're performing in a sharded environment. But as I said, it's not only NoSQL style development, it's NoSQL style development when you need it, but all the power of SQL when you need it too. One of the problems with JSON, and to a lesser extent was true with XML, was it was very good as long as the queries you wanted to write were the queries that the application developers had thought about when they developed their data model. But the problem was, what happens when somebody wanted to ask a query that wasn't thought about at the time the application was developed? There is no standard simple query language for JSON documents. And what we did was, rather than say, let's build a new one, somewhat what we tried to do with XQuery and XML, we learned from the School of Hard Knocks. We said, why don't we just make it possible to issue SQL queries on top of your JSON data? And with Oracle, that's exactly what you can do. Here's an example of how we can query JSON data using SQL. In this first example, I'm querying my theatre collection, and my theatre collection is stored using blob. Fundamentally, if you have documents that are bigger than 32K to manage, we recommend that you store them using the blob data type. The reason for that is that, hopefully by now you're all using AL32 UTF-8 databases. If not, at least for JSON, I would strongly recommend it. The one downside of that is you really don't want to store stuff as CLOB in a AL32 UTF-8 database because it's stored as UCS2, and so you're doubling the size for no real benefit. So for JSON documents in an AL32 UTF-8 database where the 32K max 32K varchar 2 is not sufficient, we recommend that you use the blob storage model. And the one downside of that is when you want to see the contents of the document in SQL, you'll need to wrap it in the toClob operator in order to see it as text. But that's just for printing it. So here we go. Give me back the document whose ID. So within that document, there is a key called ID with the value of 1. And you see here that I can simply query my JSON documents by dotting my way into the JSON structure after the column name. And the only thing I have to remember in order to do that is I do have to use a table alias. So in order to use the simplified syntax, it's table alias dot column name dot path into your JSON structure. And then you can just query away using SQL. There are some limitations to the simplified syntax. We're getting rid of as many of them as we can, but there are certain things that you cannot do easily with the simplified syntax. And for that, we provide JSON operators and JSON path expressions that allow you to do things like tell us how you want to see the data. So the simplified syntax has no idea, at query time, whether the JSON that it's going to find is varchar or, a string or number. And so everything comes back as string. With JSON value, which is the operator, you can specify the JSON path, and you can specify the SQL data type you are expecting.
Question, sorry.
Yeah, go ahead.
The first query, how does the Oracle database know that is a JSON document? Because you're not specifying it anywhere, right?
No, my column name, sorry, in this model, my column name is JSON document.
But that's not the data. There is no data type, or there is no, how does it know that that blob field is has JSON document in it?
Because so this table was created through Soda, and what Soda would have done is it will have attached the isJSON constraint.
Okay, constraint is there. Okay, thank you.
Yeah. To the column. Also in 18.1, we introduce a treat as JSON, which allows you to, if you do happen to have a table, a legacy table, or something which has JSON content in it, and you want to be able to query it using the JSON simplified syntax, there is a treat as JSON clause that you can now apply to tell the database that this should be treated as JSON. So as I said, we have, as that slide showed, we have two ways of working with JSON. One is what we term the simplified syntax that basically allows you to just use dotted notation to navigate your JSON content, and the JSON operators that are part of the SQL standard and introduced in the SQL 2017 standard, which was developed in conjunction with IBM. But both techniques use JSON path expressions to navigate JSON documents, and JSON path is derived from JavaScript. So the operators we have are is, optionally not, JSON, allows you to test whether a column has well-formed JSON in it. So typically the most common use case is I'm going to put that as a constraint on a column to tell the database it should only contain JSON. I can also use it in something like a where clause, whereas if I have a table where some of the content is JSON and some of it is not JSON, I can use it in a where clause to filter out so that the operations are only applied to those columns that contain valid JSON. The second operator is JSON value, which allows you to extract a single scalar value from your JSON document. JSON query is the antithesis of JSON value. It allows you to select arrays or objects from within your JSON documents. JSON exists, typically used in the where clause, allows you to test whether or not a JSON document contains a key that has a particular value associated with it. JSON table, if you're writing SQL queries, JSON table is the one you're likely to use most often. It basically allows you to project JSON data into a relational format in the form of a virtual table. So JSON table goes in the from clause and allows you to basically project an inline view of one or more rows from your JSON document. And JSON text contains allows you to do text-based searching of your JSON content. Here's an example, very simple query using the simplified syntax, doing something that is almost impossible in any of the NoSQL document stores. Can anybody tell me what I'm doing here that's almost impossible in the NoSQL document store?
The regular join between.
Yeah, exactly, a join. It's so obvious to us, but it's almost impossible in any of the JSON document stores that I know of. Even those like Cosmos that support a SQL-like syntax don't allow joins. They allow
how is performance when you join, do some joins like this if the document
if you have the appropriate indexes built, it's identical to relational.
In the case of relational, you can index, and here also you can index.
Yes, you could build functional indexes. If I was building this and it was something I was going to run on a lot, I would build functional indexes on the document, on the ID attribute in the theater table, on the theater ID attribute in the screenings table, and the ID attribute in the movies table, and the movie ID attribute in the screenings table, and where would I put the start time? Put the start time, one of those indexes will be a compact indexes with the start time in it. But it's, just like you would do with relational.
Sure. Thank you.
Here's an example of filtering. More complex filtering than simple or equals clause. The first one is a very simple one on the left-hand side here. I'm simply looking for documents where the ID attribute, which is found at the top of the document, matches the value of a variable called $ID. And then so that's my JSON path expression, $ question mark, open brackets, @.id equals $ID. Says look for documents whose ID, where ID is a top level key, matches the value of this variable. And then the second part of the statement passes 1 as ID. Now that might look a bit strange. Why did I bother doing that? Why didn't I just say @.id equals 1? The answer is binding. By writing it this way, that becomes a cursor with a bind variable. So I can now, if I execute a second statement where I pass 3 as ID, that will reuse the cursor. More importantly, if I was writing an application program, I would put my bind marker in place of :1. So I would put my :1 or my question mark in place of the hard-coded one, and I get binding. I get the ability to reuse the statement with different values. The example on the right is much more complex. Basically, we're looking at our movies, and we're looking for movies that run beyond 120 minutes, and where they have a crew member is an array of roles and names. And I'm looking for arrays where the crew member contains a single instance where the role is director and the name is Steven Spielberg. And this is quite important because once you have nested objects like this and nested arrays, and you're wanting to start querying them, if I say where the array contains the director, the role director, and the name Steven Spielberg, without this nesting syntax that we see, I could find the roles where Steven Spielberg was the producer and George Lucas was the director, because there would be a role called director and there would be a producer called Steven Spielberg, but it wouldn't be on the same instance. So this nested thing that you see here, where I have a crew member, question mark, and then the open parens @job equals role and @name equals name, make sure that they exist in the same instance or the same item within the array. This is actually something that's very difficult to do in some of the other NoSQL languages. If I want to query multiple values in a single statement, this is how I do it. I use JSON table to basically pivot paths out of my JSON into columns in my view. So it produces an inline view with columns theater, ID, name, street, city, state, and zip. And those columns are derived from the keys identified in the path clause of the row, or what we term the column pattern of the column clause. Here's an example where I actually have an array within my JSON document, and when I process that array with JSON table, I can actually generate multiple rows, one for each member of the array. So my theater has a collection of screens. I do a nested path on screens, and now I can project out information about each screen within the theater. So now, instead of getting 1 row per document, I get 1 row in the view for each member of the array. And once I have this, I can bring all the power of SQL to bear on my JSON data. You can see here, I'm calculating the total capacity of the theater by summing the capacity of each of the screens within the theater. A very simple SQL query, but very complex to do in a typical NoSQL database. If I have GeoJSON embedded in my JSON document, for instance, you can see here a simple example of a GeoJSON giving me a point to the location of this theater. I can convert that to an SGO geometry object using JSON value. And then I can start doing spatial queries on my GeoJSON content. Piecewise updates are possible. We have an API in PL SQL, very similar to JSON if you've used JSON from Java, but basically it gives you the ability to parse the JSON, find out what the structure of the JSON looks like, and operate on the individual pieces of the JSON. And here's a very simple example of doing that. I'm reading a JSON object. I'm creating a JSON object from my JSON document. I'm getting out the tax rate and the price, and then I'm adding to the document a new key called total including tax, which is found by price times tax 1 plus tax rate. And you can see here that it basically gives me the ability to create a new object or to insert a new key into an existing object using the PL/SQL API. Dataguide, I think that's the last thing I'll have time for today. Dataguide is a really powerful capability. It allows you to understand what your JSON documents look like. Basically, once you've stored a set of documents in the database, you can generate a data guide and it will give you a report of what the structure of your JSON looks like. There are two variants of the JSON data guide. There's what we term a flat version, which basically gives you a list of all the keys that it has discovered with the path between the top of the document and the key. And there is a hierarchical representation, which is a JSON schema, which basically lays it out that, we have a key called A, and within that there's a key called B and a key called C. There are two examples. On the left-hand side, you have the flat representation, and on the right-hand side, you have the hierarchical representation. There are two ways of creating a data guide. One is what we term a snapshot, where basically there is a function JSON data guide, which will return this, and you can return it, you can just select it from a table. On the left side format flat, on the right side format hierarchical. The advantage of this is that you can use SQL to filter and group the documents, so you can get a data guide on a particular subset of the documents in your data, in your table, using the JSON data guide functionality. It fundamentally, although it's not obvious, it's an aggregation function in SQL terms. There's also what we term the dynamic JSON data guide, which basically uses an index to capture the information about the changes in the data. The advantage of the dynamic data guide is that it can do things in real time. So for instance, one of the things we can do with a dynamic data guide is we can add an on-change option to the data guide, which says, when you detect a new key, call some procedure you provide. We've seen use cases for this. Was one of our customers came to us and said, we have a standard that says thou shalt not put credit card numbers and social security numbers into your JSON data. And our application developers keep doing it. So basically they wrote a JSON data guide on change procedure, which said, if I see a new key and the value looks like a credit card number or the value looks like a social security number, then I'm going to throw an error and prevent the insert from happening. One use of the dynamic data guide there. Why would you want a data guide? It gives you the ability to do SQL-based reporting and analytical operations on your metadata. It also allows you to generate relational views of your JSON data. We can automatically build you a view of the JSON data by using the information in the JSON data guide. We can also use it to expose JSON content as virtual columns. We can automatically add new virtual columns to your table that contains your JSON data based on the data guide discovering that there is a new key has been added to the data. And it can be used to audit the structure and prevent changes to the structure, prevent certain stuff from being inserted into the JSON column, should you wish to do so. Here's an example of using SQL to query a data guide. You can see here that I'm simply generating the data guide and then pivoting rows out of it using JSON table. Here's an example of creating a view on top of a JSON content. So by simply saying create view on path $ID, it's going to give me a view that contains all of the nodes that are peers of the ID column. So instead of having to know how to write all the syntax and the JSON table operation to create that view, I can just call the DBMS JSON create view on path, and it will generate the view for me automatically. I can also do that over an array. And I can also rename the columns so that the columns get meaningful names. Here's an example of adding virtual columns. Basically, in this case, we are adding virtual columns to the screening table whenever a new key appears in that table. And finally, an example of auditing. An on-change procedure is called whenever a new path is discovered. And I think at that point, I'm pretty much out of time.